Hey everybody. We're going to talk about Green's theorem, which is a way of relating line integrals with double integrals. Now, Green's theorem is stated right here. We're going to state it, and we're going to talk about some of the terms in it. So if you have some curve, a positively oriented, piecewise smooth, simple, closed curve in the plane, and D is a region bounded by C. Okay, so here's the idea. This is what it means for it to be piecewise smooth, even if it has some corners, that's okay. Okay, so this is, as long as there are, you can kind of chop it into a couple pieces where it's smooth. Simple closed, okay, we've talked about simple closed, no holes, and positively oriented, which means that the curve is oriented in a counterclockwise fashion. Okay, so this is like the direction that the curve is, that the curve is going, and we say that D is the region that's bounded by C. So if P and Q have continuous partial derivatives, and P and Q aren't related to C and D, they could be just some functions. P and Q are functions of x and y. And as long as they have continuous partial derivatives on the open region containing D, then the line integral over C of P dx plus Q dy is equal to the double integral over the region D of the partial of Q with respect to x minus the partial P with respect to y dA. That's supposed to be a lowercase y. And this notation of a integral over a closed curve, sometimes you'll see a notation, sometimes a little arrow indicating the counterclockwise rotation. So this is Green's theorem. So if you need to calculate a double integral, you can sometimes calculate a line integral instead, and vice versa. So here's an example. Let's look at the integral of this function where P is x to the fourth and Q is xy. So we're integrating x to the fourth dx plus xy dy, and C is a triangular curve consisting of line segments from, so here are the points. We have 0, 0, and we're going to 1, 0. Okay, so we're going to go in that direction. And then we're going to go from 1, 0 to 0, 1, so that's up here, 0, 1. And we're going to go back down from 0, 1 to 0, 0. So this is it. Now, what this says is this line integral is equal to the double integral over the region D of the partial D of partial Q with respect to x minus partial of P with respect to y dA. So what is this? This is going to be y minus 0. It's just y minus 0 because P is x to the fourth, so there's no y's involved. And we could set up the bounds of this integral. We've done this before. We can have, for example, x going from 0 to 1, and we can have y going from 0 to 1 minus x. That'll work. And we're just integrating the function y. So this is the integral from 0 to 1 of 1/2 y squared from 0 to 1 minus x dx. So this is going to be the integral from 0 to 1 of 1/2 1 minus x squared dx, right? And the integral of this is going to be 1 minus x to the third, but we're going to have a 1/6 now. Of course, the chain rule would give us a negative, so actually it's going to be negative from 0 to 1. So we're going to get, at the upper bound, when x is 1, it's going to be 0, and so it's going to be 1/6 times 1 to the third. So altogether, this is 1/6. All right, let's look at the integral over the curve C. A circle with radius 9. So here's the picture, right? Oh, sorry, not radius 9, but radius 3. And the function is 3y minus e to the sine x dx. So p is this, and q is here. And so the line integral over this closed curve is going to be equal to the double integral over the region D, right, of partial q with respect to x, minus partial p with respect to y. So this is going to be a lot simpler because you can see already that q, the portion of q that's a function of x, is very simple. This is the integral of, I'll just do the inner part first, then we'll talk about what this, how we'll parameterize this. We'll do this integral, right? So the function we're integrating, partial of q with respect to x is just the number 7, and the partial of p with respect to y is just the number 3. So, and this is ripe for polar coordinates. So we can go from 0 to 2 pi, and radius from 0 to 3. So the function we're integrating is just 4, right? So it's going to be 4r dr d theta. So we've got no theta, so I'm going to just put the 2 pi there, and this is going to be r squared. The 4 is going to be 4 over 2. It's going to be 2 r squared from 0 to 3. Well, okay, so we're going to have 2 pi. Actually, let's just write it. It's 4 pi times 3 squared, right? And so that's 9 times 4 is 36 pi. So if you're integrating, if the integrand is 1, if you want to find the area of a region, so if you want partial q over partial y minus, or sorry, partial x minus partial p over partial y, if you want that to equal 1, then you're able to, then you'd be integrating 1 dA, right, over some region. So if you can parameterize the boundary, the curve that gives you the boundary, you just have to find a p and a q that'll work. And here are some possibilities where this difference of partial derivatives equals 1. You can, for example, let p equals 0 and q equals x. You could let p equals negative y, q equals 0. You could let p equals negative 1/2 y, q equals 1/2 x. These are a couple possibilities where the difference is going to be 1. There are other possibilities, of course, too. So yeah, so this is a the area, this corollary actually is just the Green's theorem saying the area of some region would be equal to the line integral over C of x dy, or negative integral of y dx, or 1/2 the line integral over C of x dy minus y dx. So any of those would work. So for example, let's find the area enclosed by this ellipse. And so for this ellipse, right, we can write this ellipse as, let's see, we can let x be x be a cosine theta, y can be b sine theta, and we can, and theta is sort of our, we can let theta go from 0 to 2 pi, right, over this curve C. So this is going to give us this ellipse that's going to be crossing at a and negative a for x, b and negative b for y. I don't know, let's just pick the first one. Let's take the integral of C of x dy. Okay, So this is going to be from 0 to 2 pi. X is going to be a cosine theta and dy. But when I say, what is dy? let's figure that out. So dy is going to be b times cos theta d theta. Right? So this is actually integral from 0 to 2 pi of ab cosine squared theta d theta. Do you remember what the integral of cosine squared is? Remember, this is rather than going through this whole thing, the cosine from 0 to 2 pi, remember, it just creates the full period of the cosine function, but it's going to start at 1, and it starts and ends at 1, so it's going to go down to here, so it's going to, because it's going to be squared actually, this at pi, it's also going to be at 1, so it's going to go up and down, it's going to fill, it's going to be this region here, right? Which is exactly the same area as the region that's not shaded up there. Well, the full rectangle is 2 pi. Half of that is going to be pi. So this is going to be a, b. This is the area of an ellipse. If a equals b, then this is pi r squared. So if you have a region that is not simply connected, like if there's a hole, what you can do is you can split cover the entire region D, or region R in this case, call it R. You can have kind of partition it into non-overlapping simple regions, and so you can kind of, as long as you can, you have the inner circle has the opposite orientation as the outer loop, right? You can see you could, by going in, we're gonna go this way, we're gonna come around, we're gonna go around here. So this is gonna be the first counterclockwise. That's the positive orientation. Then you create another positively oriented curve, C1 and C2, and then you're able to use Green's theorem on you can split the region into a sum of two integrals. So here's an example of that. So f is given here. It's negative yi plus xj over x squared plus y squared. So we want to show that the integral of f dot dr is 2 pi for every positively oriented simple closed path that encloses the origin. So here's the idea. So suppose you make some positively oriented simple closed curve. This is C, right? And it's positively oriented. We want to show that the integral, we want to show that the line integral over C of f dot dr is going to be equal to 2 pi. What we're going to do, so what we're going to do is, so say you have some arbitrary curve C. What we're going to do is we're going to make another curve which contains the origin, and this curve is going to be a circle. Okay, so this is going to be a circle, and it's also going to be positively oriented. And so what we're going to, so this, I'll call this, call it C1. And so that we'll call the region that's between the two, this region here, call this region D. So because this, let's just copy it over. I can actually cut this into, let's see, let's do it in green. So if I were to make a cut across here, it doesn't really matter where, and if I was to go in this direction here around the top curve and then cut it in and then go in the opposite direction, right? That would be one curve I can make, and then the other one would be coming up. It would be going this direction. All right, and so altogether, what I've got here, because the line integral from this point here to this point, I'm going in one direction and I'm going in the other direction. The integral over the region D of partial q partial x minus partial p partial y dA is equal to the line integral over c of p dx is q dy minus the integral over c1 of p dx plus q dy. All right, so this is to say, like, the integral, double integral over the region D, it can be partitioned into the two parts, where you can see the line integral that goes around the first part goes in, we're going in the negative direction on C1, and then we're going in the, and in the bottom part, we're also going in the negative direction of C1. Now, we are given, so P is negative y over x squared plus y squared, and Q is x over x squared plus y squared. So what we're going to do here is we're going to, so I'm going to actually, I'm not going to figure out exactly what this is first. This is really our goal, right? We're trying to figure out what this thing is. Let's do the partial of q with respect to x, right? We're using the quotient rule, of course. So we're going to have 1 times x squared plus y squared minus x times the derivative of x squared plus y squared. That's going to be 2x all over x squared plus y squared squared. This is actually going to be y squared minus x squared over x squared plus y squared squared. And so this integral here over region D, we've got for partial q partial x is y squared minus x squared over x squared plus y squared squared minus, now what's partial p with respect to x? Partial p with respect to x is going to be negative y, or it's negative x squared plus y squared minus y times y times 2y. The derivative of that is going to be a 2y. Okay, and so what we've got then, 1 second. Oh, it's minus, so it's going to be plus y. So this is going over x squared plus y squared squared. This is going to be y squared minus x squared over x squared plus y squared squared. So what we're going to be subtracting is y squared minus x squared over x squared plus y squared squared dA. This is actually the integral of 0, so this is actually 0. What this means is that integral over c of p dx plus q dy is equal to the integral of over c1 of p dx plus q dy. Now we can actually evaluate this integral over c1 because this is a circle, right? And this is going to be, we can parameterize this. We can say, we can let x equals whatever the radius of that little circle is, call it r cosine theta. Let y equal r sine theta for whatever that r happens to be. It's something small, right? And then, so we're looking at the integral from 0 to 2 pi, right? P is going to become negative r sine theta over x squared plus y squared, which is going to be r squared. This is d, now what is, I'm going to write it here and I'm going to go to the next page. This is dx plus q, which is going to be r cosine theta over r squared dy. Well, let's go to the next page. So remember, x is r cos theta. So dx is r, it's negative r sine theta d theta. Y is r sine theta. So dy is r cos theta d theta. We plug all this stuff in, what we're going to get, integral from 0 to 2 pi of negative r sine theta and then negative r sine theta d theta over r squared plus r cos theta over r squared, and then we have an r cos theta d theta. This is, you can see all the r's, these r's cancel, What you get is the integral from 0 to 2 pi of sine squared theta plus cosine squared theta d theta. Lo and behold, right? This is going to be the integral from 0 to 2 pi of 1 d theta, which is 2 pi. Remember, we said the integral of f dot dr over c was equal to this. So it's equal to 2 pi. And that was regardless of the curve. Curve c was arbitrary for this particular function, right? And that's it. So that's what we're going to cover here for Green's theorem. We'll do some examples of this in class. Ciao.